So we decided to put my view of 40 years into 20 minutes. Unfortunately, I've got 40 years worth of slides here, so they're like, here's what I think we're doing today, and I'm basically just going to repeat what Paul said. We want to gather innovation lessons, and I've begun writing them down. I have 4 of them so far. We're going to hopefully sing Ethernet's unsung heroes. And it's true, I've got much more credit for Ethernet than I deserve, and the other people who are a little annoyed about that are here in the audience today. I'm bring them forward. Then we're going to have a party, and then tomorrow we're going to catch up on what I believe is about $100 billion industry that calls itself Ethernet. So depending on the meaning of the words I and invent and Ethernet, there are some values of those 3 variables for which I can say I invented Ethernet. And I'm going to, in the midst of this talk, since there's a lot of bogging down in what the word Ethernet means, I'm going to explain exactly what it was, a very small thing, that I and Dave Boggs and David Liddell and Tat Lamb and John Shaw actually invented at Xerox PARC, which is one of the many meanings of the word Ethernet. Of course, Ethernet is now a brand that has escaped that, so I hope to get to that. There'll be a lot of technical detail during that portion of the talk. So here's the bigger context for Ethernet's invention. This is the history going back to ARPANET all the way through today. As you can see, I wrote this by hand, and then I photographed it, and then I uploaded it into PowerPoint. And I went through those steps because when Ethernet was being invented, PowerPoint did not exist. So this is how we made slides that we would photograph into the 35mm camera. Key events here, you see the ARPANET, Internet 1.0, you see the invention of Ethernet in '73, the LAN Wars from '81 to about '84, we'll talk a little bit about. Fast Ethernet coming out in '95, we call 100 megabits per second hour, we call that fast. And then what followed. So we're talking about a small part of a very long history. You can't see that, but that's the cover of my PhD dissertation. But what's noticed is the map of the internet. Can you make that out at all? You see those dots? Those dots are not cities. Those dots are not buildings. Those dots are computers. That's how many computers there were on the internet in 1973. You can count them. Now, I'm now a professor at the University of Texas in Austin. I love to show them this because you'll notice the internet goes through Texas without actually stopping there. And what we were involved in at Xerox PARC is called distributed computing. That was the term. For example, the course I taught at Stanford had that term in it, distributed computing. And basically we were going from a box-centric view of the world in which there were lots of little terminals connected to a big box in the center, to a net-centric world in which the network was in the center. I'm not sure when we first started calling the network the cloud. Of course, it's now, the cloud is used everywhere, but the network was in the middle. That's the picture. What I wanted to point out in this picture that you just saw a moment ago, so on the right is the Texas Instruments Silent 700, which we all had one of at Xerox PARC. And its modem, acoustically coupled, ran at 300 bits per second, 30 characters per second. In the middle, at the top, is a box of 35mm slides. That was the method we used for giving presentations, overheads and 35mm slides. And you'll see right in front of me there is what's called a Rolodex. So people had Rolodex. I had Rolodex for a very long time. I still have it, by the way. They came really big after a while. And then you'll see there's a telephone there. Over here are some pads on the lower left, but those aren't iPads. Those are just regular pads. So let me describe the innovation space in which that aforementioned group of people were operating. Try to recall, this is the space in which we were attempting our innovation. We were were going to put personal computers in a building, the Xerox Alto. The notion of having a computer on the desk was at that time controversial. Having a building full of PCs was, that may be the first time that ever occurred. And our great fortune was to be given this problem that had not previously existed. What do you do with a building full of personal computers? So about hundreds of machines spread out over a kilometer, one per desk. They had to be small and cheap. Cheap meant the computer cost $30,000. And we were going to be upgraded, going from the Silent 700 to the PC. And we ended up going a factor, the networking ended up going up a factor of 10,000 in that one step. Second, the applications we had in mind. We were building a network, well, first of all, these PCs were replacing Silent 700, so they should do at least what the Silent 700 did. So we needed to, so I wrote Telnet for the Alto. You all know what Telnet is? So we needed Telnet on the Alto so we could go log into machines around the internet. And then we were building a laser printer called EARS, 500 dots per inch, page per second. You multiply 8.5 times 11 times 500 times 500 per second, and you get about 20 megabits per second. And we wanted to keep the printer busy, so the network had to be a significant fraction of 20 megabits per second. And we also had this general notion, which is associated with the overall effort of producing PCs, that if we built it, they would come. That is, we were not really good at listing what the applications were going to be for all this, but there was a build it and they would come mentality. And that has happened. So in the history of Ethernet, every time we've built it, they have come. And by they, I mean the new applications. Now, we also had some digital technology to play with. And I sort of put up defensively, because I'm frequently approached by young engineers who say, why did you do Ethernet that stupid way? And the answer is we didn't have LSI. We had MSI, medium scale integrated Texas Instruments 7400 series semiconductors, in which, for example, you could get 2 flip-flops on a chip. So so we had FIFOs, which we needed to get the data in and out of the computer. Those were pretty integrated. David Boggs found a CRC chip to check whether the bits had been damaged in transmission. The MOS memory is what enabled the Alto, and that was a PARC called the 1103 from Intel that had 1,000 bits on one chip, at a penny a bit, roughly. And that was a big enabling technology. And then we had this tasking microprocessor, the Alto itself, to play with. And we wrote our programs and protocols in BCPL and assembly language. So that was the enabling digital technology, and I put that up mainly as an excuse for some of the stupidities of the early Ethernet, because that's all we could do. We didn't have LSI. And then there was the wire. So that I had just finished putting MIT, a part of MIT and Xerox on the internet with a cable about this thick, called the IMP cable, that went from the mini computer into the packet switch. The cable was this thick, and when I put it on my board, I had to bolt it because it was very heavy. It could easily break, and strain relieve it with cable ties and so on. And then so cabling was a problem, and our building had a rat's nest full of cables in it, which was a problem. So it was very much on our mind to solve the cabling problem. And then we found the Aloha Net. I noticed Norm Abramson is here, the inventor of the Aloha Net. And it had 2 radio channels, so I went on an expedition, a field trip. I spent a month in Oahu at the University of Hawaii studying the Aloha network. I recommend that field trip. So we wanted to solve the rat's nest problem. We had a large number of cables that would be very long, and they could end up being thick with big unreliable connectors. And the speed had to be faster than 300 bits per second, faster than the Aloha network, which is about 9,600 bits per second, faster than the ARPANET. The ARPANET, we were really only getting 15 kilobits per second in and out of our time sharing system. But we had this damn printer, and it was running at 20 megabits per second, so that was driving the speed. So we decided to choose a medium that had one wire. We looked at 0, by the way. Aloha network had 0 wires. The trouble is the modems were as big as this podium, right, Norm? And we needed to put one on every desk, so that wasn't going to work for us. And plus we needed to run at megabits per second, so I hope you don't mind. We switched back onto wires, but only one of them, which we call the Ether. And then there was the sharing part. So imagine 256 computers spread around the building. Where would they, as the data is going back and forth, how would that be clocked? Tick, 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 data, data, data. Would there be one clock, or would there be a distributed clock? And we decided we weren't going to have a big central clock. The network was going to be completely passive, which meant the clocking of the data had to be in the data. And then we needed to arrange for the stations to take turns. They had this one wire, but they had to take turns using it. How were we going to do that? And then it had to do that efficiency with low latency and fairness. And it was in the context of that I ran across a paper by Norm Abramson at the 8th FIPS conference proceedings at the Fall Joint Computer Conference in 1970. And it had math in it, this paper. And that was important, first because it was math that I could understand, but second of all, Harvard wanted my thesis to be more theoretical. And you had math in the paper, so I said, aha, theory. And in that was the math of randomized retransmissions, which I'll return to in a second. And then we needed reliability. We're going to have a big cable running through the building that everything was going to be connected to. Wouldn't it be terrible if somewhere in the building that cable got grounded or shorted or broken? So a lot of energy went into making the reliability of the connection there very high. And a man named Tat Lam, who I haven't seen for 20 or 30 years, he engineered that. He kept telling us it had to be under 4 picofarads. And that's all I remember, 4 picofarads. And so he achieved that with a transceiver. And so the transceiver could be on, but then it had to mostly be off. And it had to be safely off. Its default mode had to be off, letting go of the cable so the packets from other stations could zip by. Then in hardware, Dave found the CRC chip, which was the last things to squeeze on the board. We also had a software. We had a software checksum because we weren't sure that the Alto was that reliable. So we wanted to be sure that the bits got all the way into memory and not dropped by one of the MOS memories we were using. So we had a software checksum. And then there were the protocols. And this is key because we realized that the Ethernet, this network, would exist in a hierarchy of protocols with 7 layers. And then we came to rely on those layers, simplifying our design. So for example, the Ethernet had no acknowledgements in it. There were no acknowledgement packets. They were just packets. The higher level protocol would create the acknowledgements. So we didn't have to, which made Ethernet simpler. So now I'm coming to the exact thing that we invented. We came across a method of encoding called Manchester encoding, which had the feature that in each bit cell, the first half of the bit cell would be the bit, and the second half of the bit cell would be the complement of the bit, guaranteeing that in the middle of the bit cell, there was a transition from bit to bit bar. And that transition would be the clock. So the clock was encoded in the data, and it came in the middle of every bit cell. And another cool thing about this encoding was that the cable was either on or off. You see, you could drive the cable to say 5 volts. David, what was the voltage? 3.5, thanks. 3.5 volts, or you could ground it, or you could let it go. And so in the case of Manchester, there were only 2 states, yanking it up to 3.5 volts or letting it go. So half the time, while you were transmitting, you were letting the cable go, which had very important consequences. It gave us huge advantages over the Aloha network, because the Aloha network couldn't listen to what it was doing. It could only deduce what had happened after the fact, and this gave us great advantages. So with Manchester encoding, we then go to the Aloha paper. So the idea was the stations were going to put packets on the ether, and if they got through, fine. If they didn't, they could retransmit, like the Aloha network taught us. So I looked at Norm's math. And 2 things about it were annoying, Norm, as you know after my complaining for 40 years. There's one, he assumed the network had an infinite number of users. kept on typing even if the packets got lost. And I knew that the Aloha network had 6 users, which is a lot less than infinity. And people would stop typing if the packets didn't get through. So in the process of simulating this to see what the numbers really were, I wrote a computer simulation of the Aloha network. And there came this awkward moment in writing the code where I had to specify the mean of the retransmission interval. And Norm's math did not have any such thing in it. So that was the first departure. I actually had to specify what the mean of the retransmission interval was. And then I started running the simulations, and I started noticing that every time I ran the simulation, even with all the parameters constant, I got a different answer each time, which meant that the state space of the channel was bimodal, the right-hand diagram. That is, Norm's math that dealt with the average, but as you can see, the average is very unlikely. It's in the middle of this big valley. So then we applied Manchester, and this is it, this is the thing, this is the invention right here, Manchester encoding to make that channel stable. And we did it like this. Because we had Manchester encoding, every time a packet was going by on the network, you could tell within a bit time by just listening. Just listen to the cable and you could hear the Manchester. And if there was somebody already transmitting, that was not a good time to start. So we could avoid collisions by just listening first. That was called carrier sense. And then because the network was off half the time when you were sending, while you were sending your own packet, you could be examining whether anyone else was sending in the half bit cells of each bit. You could listen and tell if there was a collision. So we had collision detection, and the radios of the Aloha network couldn't do that. And then our packets weren't just card images, 80-column card images. They could be really big packets. So the ratio of the packet length to this collision avoidance mechanism is very large. So we could amortize one collision interval over a very long packet. So we were therefore able to get high efficiencies. And then one more thing. How do you get the channel stable? And what we discovered is if you hit too much traffic, the proper instinct was not to try harder. You send a packet and it gets collided. You don't try harder. What do? You back off. You try less hard. You back off. And so back off. So you all see this was the invention, that group that I mentioned before. That's what we came up with, using Manchester encoding with the constraints that I enumerated prior. And this is where the Aloha network came in, taught us how to do randomized retransmission. And what we added was the fact that we were on a cable and this back off thing. So that led to this memo written on May 22nd. And I like showing this because I really like annoying the people who invented Wi-Fi. Because there's 4 or 5 of them arguing about who invented it, and I've met them, all of them, and they're always kvetching about who invented it. Sort of like the Ethernet people, who invented Ethernet. And I've explained exactly what we invented. We didn't invent everything else. So what I do is I generally claim to have invented Wi-Fi, too. And you see on this diagram on the far right-hand side, what does that say over there? Radio ether. Well, what do you think that is? Well, it's either Aloha network, which is probably what I had in mind, or it's very long-term anticipation of the arrival of Wi-Fi, and therefore I invented it, for those of you who So this is where we decided to call it the ether. We chose thick coaxial cable because it could be tapped passively, but we anticipated other media would be used, so we didn't call it coax net. We called it Ethernet because the ether could be coax, twisted pair, radio, optical fibers, and a power line, whatever you want. And that was a diagram in 1976 of what we built. That big yellow thing is the cable. The official color of Ethernet is yellow. And of course, this bears no resemblance to the Ethernet that you're using today, in which that big yellow cable has been collapsed to a box and the rat's nest has been recreated. that's the original transceiver by TapLAN, the Gerald cable tap suggested by David Liddell, this thick coax. Was it 50 or 75 ohms, David? 75 ohms, and then we went to 50 ohms later? Very important technical factor, the ohms in the cable. It's also a half-inch thick, which was later a problem. I saw this exists yesterday. This is the Ethernet at Xerox PARC, at PARC, which was near where the Ears printer was. And this is Dave Boggs on the left and Ron Kern. So Dave Boggs and I invented, with the other people I mentioned, did the work of building the first Ethernet. Ron Kramer in the back, he's the one who picked it up at Xerox later and joined me at 3Com Corporation to make it an IEEE standard. And then followed the LAN Wars, and these are some of the weapons of the LAN Wars. Promotion, which is standards are a good thing. Join, get on the Ethernet bus. I'm plugging Ethernet, etc. That lasted 2 or 3 years. And then 2 things happened that helped. One was the arrival of the IBM PC in August of '81. Finally, a PC worthy of Ethernet. That is, the 8-bit Apple II was, the Ethernet was a gross overkill for an Apple II, but it worked for the IBM PC. And then the other breakthrough happened in the late 80s was the switch from coax to twisted pair. We were fighting in the market with the IBM Token Ring, which used twisted pair, and the customers kind of liked that, so Ethernet decided to become twisted pair too, and that sealed the doom of the Token Ring. So now where is Ethernet going? Have I run out of time yet?
Keep going, Bob.
Keep going? So here's, Ethernet is not done yet. So here are the 5 directions in which, there are probably others, but these are the 5 I thought of, each with its own preposition. Up, into, over, across, and down. So Ethernet as the LAN continues up, and the IEEE has recently started a project to standardize 400 gigabit per second Ethernet on its way to terabit. Ethernet has also left the LAN and entered the WAN, where it is slowly wiping out SONET, which was the previous LAN or WAN infrastructure. That is, in the early days of the internet, we relied on the telephone company. Now we don't so much anymore. It's gone over the airwaves, hence Wi-Fi, across the telecasm, thanks to the MEF, the Metropolitan Ethernet Forum. Ethernet has now become a service offering of the carriers, going across the telecasm between the LAN and the WAN. And Ethernet, under many names, is now going down. We're now going to network embedded microcontrollers, about 10 billion of which are shipped every year, and most of them are not networked yet. That's being taken care of now. So that's where Ethernet's still going. And then let me just close with the innovation, my view of the innovation horizon ahead. As you know, the internet, with Ethernet as its plumbing, has disrupted a series of industries. You know, like music, books, telecom, television, you name it, there's a bunch of them. Well, there's 3 more industries about to be disrupted. And they'll be disrupted by these new kinds of traffic. So down the left, you have the new kinds of traffic, video, mobile, and embedded. And then across the top, you have the 3 new industries to be disrupted. These industries are begging to be disrupted. They can't wait. Energy, healthcare, and education. And so what I find it useful to do is to look at each of the boxes there to see how will that traffic disrupt that industry. And it's in those boxes that we find the needs for ever faster, better Ethernet. So that is the end of my